So here I'll begin with modeling and similitude studies. Okay,
Mhm.
modeling and similitude studies.
Mhm.
So here,
And today I'm only available for 2 hours.
okay, fine.
Yeah.
Yeah. So see here, models are generally models are generally smaller version of smaller version of prototypes. Prototypes. The experimental results the experimental results obtained from the model tests may be may be transferred to the prototype by use of model laws. By use of model laws, which may be which may be not defined developed, which may be developed from the principle of similitude. So whatever I explained you in the beginning of this dimension analysis, the very same thing here I have written. Okay.
Mhm.
So instead of testing prototype, which is larger one, we prepare models, and these models should similar with prototype. Similar in sense, three types of similarities are there. What are those three types of similarities?
And the prototype and the
Yeah.
model,
Yes.
the similarities, the forces.
Geometric similarity,
Oh,
kinematic similarity, and dynamic
yeah,
similarity, right?
and dynamic similarities. Yeah.
Yeah. So these three similarities should satisfy between model and prototype. In such a
Yeah.
way, we are going to prepare model, right? After preparing the models, we carry out the experiments on models, right?
Yeah. Yeah.
And these experimental results are transferred from model to prototype by using some model laws. Okay.
Yeah. Okay.
Now, what
Yeah.
are the model laws here? We are going to discuss mainly in our course. In our course, the model laws that we concentrate are Reynolds model law and Freud's model law. Okay.
Yeah.
Did you remember that? Which is what I explained in our last class as well.
Yeah, yeah. I remember we were talking about the dynamic parameters as well, dynamic,
Yeah.
kinematic, and the other one, which was
So that also I'll write it.
dynamic,
Okay. Don't
kinematic,
worry.
and geometric. Those
Yes. Yes.
variables that we were also talking about
Yes. Yes. Whatever you said
last
is
class.
correct. So everything I'll write it. Don't worry. Okay.
Yeah. Hmm.
So Reynolds model law implies Reynolds number for model should equal to Reynolds number for prototype. That is Reynolds number for model is equal to Reynolds number for prototype. Okay.
Hmm.
So this is the first model law, and the second is Freud's model law. Freud's number for a model is equal to Freud's number for a prototype. That is Freud number for model is equal to Freud number for prototype. Okay. So these two are the model laws we use in our course, right?
Hmm.
Here they seems to be very easy, but in questions, the relevance you understand. Okay. Here, as I
Yeah.
said, they seems to be easy and simple, but in questions, you realize the importance and relevance of these simple model laws. Okay.
Hmm.
Right. And along with, let me write the types of similarities as well.
Yeah.
So as we know, how many types of similarity should exist?
3.
Three. Yes. What are those?
Dynamic,
Geometric,
kinematic, and geometric.
geometric similarity, kinematic similarity, and then dynamic similarity. Okay, these are the three types of similarities. Now, let me draw here a small diagram of prototype and model. Let this be the prototype, okay?
Mm-hmm.
Let this be the prototype. And we know that model is a small scale of prototype, right? Small scale
Yeah.
version of prototype.
Mm-hmm.
So let me draw the model of this prototype. Right, this is the model, okay?
Yeah.
Now here in prototype, I'll consider some points. So point 1 I'll consider on top face, okay?
Mm-hmm.
And point 2 on side face. Because
Yeah.
here I consider on cuboid, which is having 6 faces. Top and bottom, right and left, front and back, isn't it?
Yeah.
So now the third point I'm considering on the back face here. And fourth point I'm considering on right face here, okay?
Yeah.
So total I've considered 4 points. One is on top face, and other is on left face, third is on back face, and fourth is on right face, isn't it?
Yeah.
And this is the length. Let it be the length of the prototype LP, okay?
Yeah.
And this is the width, or you can say breadth. So width of the prototype, and this is height. Clear?
Yeah.
Now here coming to the model, same point I'll consider on top face, right side face, so left
Mm-hmm.
side face, and back face and right face. Okay.
Yeah.
Then this is the length of the model LM, and this is the width of the model BM, and this is the
Mm-hmm.
height of the model HM. Clear?
Yeah.
Now here 1 comma 2 comma 3 comma 4 are called as homologous points.
Mm-hmm.
Are called as homologous points. So what is meant by homologous points? Homologous point means corresponding point in the model and prototype.
Mm-hmm.
So what are homologous points? Homologous points are the corresponding points in the prototype. Okay.
Mm-hmm.
Now here in our case, what are the homologous points in our example? 1, 2, 3, 4 are homologous points, right?
Mm-hmm.
Now let us try to understand clearly what is geometric similarity, what is kinematic similarity and dynamic similarity for the model and prototype here we have taken. Okay.
Yeah. Okay, so I have a question.
Yes, tell me.
So the one is at the top,
Yes.
the 2 and 4s are on the side, and the 3s at the back, right?
Yes, yes.
So do we do anything for the bottom or the front?
Yes, of course you can take it. Here I have taken only 4 points. If you want, okay, let me take that as well. Nothing wrong. Okay, here I'll take 5 and
Yeah.
here and front face
Like
I
how
take
does that
6.
change it?
Sorry?
Does that change anything?
A change in say anything in sense if you consider more homologous points, then accuracy increases.
Okay.
That's
Okay.
it.
I see. Okay.
Okay, yeah, as per your wish, okay, nothing wrong. Here I am considering 0.5 on bottom face and on front face 0.6. Yes, if you want, you can
Yeah.
consider nothing wrong.
Okay.
Okay,
Oh, yeah. Okay.
yeah.
I see.
So now, geometric similarity. So, geometric similarity exists between the model and prototype if the ratios of corresponding length dimensions in the model and prototype are equal. Such ratio is defined as scale ratio. So, as per the geometric similarity condition, ratio of the length in model to the prototype should equal to ratio of width in model to the prototype, which should equal to height in model to the ratio of height in model to the prototype. Clear? Basically, this is called as length scale ratio.
Yeah.
This ratio should remain constant for any model and prototype. So this we represent with LR. Okay,
Mm-hmm.
this we represent with LR. Next is area scale ratio. In this geometric similarity itself, we are having area scale ratio.
Mm-hmm.
So area scale ratio we represent with AR. Whatever might be the different formula for the areas we are having based on the shape. If it is a rectangle, it is the product of width and length, right?
Mm-hmm.
If it is a square, what is the formula for area? It is simply square of the length or square of
Yeah.
the side, right? If it is
Mm-hmm.
area, then it is pi r square, isn't it?
Yeah.
If it is triangle, it is half into base into height, isn't it?
Yes. Yes.
So from this, what I want to conclude, area of any shape, be it a rectangle, triangle, square, pentagon, whatever might be the shape, it is simply the product of two dimensions, isn't it?
Yeah.
Therefore, here I can write area scale ratio as area of the model by area of the prototype, which can be written as LR square. Can I write like this? So
Yeah.
here this LR represent length scale ratio square. Okay, this is length scale ratio.
Mm-hmm.
Clear?
Yeah.
In the very same way, volume scale ratio VR is nothing but LR cube, isn't it?
Yeah.
That is volume of the model by volume of the prototype. Clear?
Yeah.
So these are the things related to the geometric similarity.
Mm-hmm.
Now next is the kinematic similarity.
Yeah. Can you scroll up for a second? I missed a
This
thing.
one? Yeah,
Yeah. Okay, yeah, I got it now.
yeah.
And yeah. Okay, I got it.
Yes. Kinematic similarity. Kinematic similarity exists between the model and the prototype if first the paths of the homologous moving particles are geometrically similar. Second, the ratio of the velocities and accelerations of the homologous particles are equal. So what does it mean? This diagram here I'll take. So see here, suppose I'll consider particle 1, right?
Yeah. I never got a little bit of the last sentence. Just
Which
a
one?
little bit. The last sentence that you
This one.
wrote for, yeah, velocities and stuff. And okay, I got it.
Okay. So see the first point. What is the first point? The paths of the homologous moving particles are geometrically similar. It means,
Mm-hmm.
suppose I'll consider here I'll take a point 1. The particle that is passing through point 1 is having path like this. Okay.
Yeah.
Now for the model also, the path of the particle 1 should be in the same way.
Yeah.
That is the meaning of the first point. Okay.
Yeah.
And after that, the second one you see, velocity at point 1 in the model divided by velocity at point 1 in the prototype should equal to velocity at point 2 in the model should equal to velocity at point 2 in the prototype,
Yeah.
and so on, right? What, how many points you may consider, all those ratios should equal, and this is known as velocity scale ratio. What this is called as?
Velocity scale ratio.
Yes, this is called as velocity scale ratio.
Mm-hmm.
Next, in the same way, acceleration at point 1 in the model divided by acceleration at the point 1 prototype should equal to acceleration at point 2 in model divided by acceleration at point 2 in the prototype, which is equal to acceleration scale ratio. Okay,
Mm-hmm.
this is equal to what?
Acceleration scale ratio.
Acceleration scale ratio, right?
Yeah.
So if these things holds good between model and prototype, then we can say they are kinematically similar, right?
Yeah.
Now we are having one more. What is that? We are having one more, that is dynamic similarity, isn't it?
Yeah. Mm-hmm. Yeah. Dynamic similarity. You did the kinematic, geometric, and just dynamic is left.
dynamic similarity exists between model and prototype exists between model and prototype which are geometrically and kinematically similar if the ratio of all the forces ratio of all the forces acting at homologous points are equal. Yeah, once you please go through it.
Uh, Dynamic similarities exist between model and prototype, which are geometrically and kinematically similar if the ratio of all the forces acting at homologous points are equal.
So what does it mean? For us to apply dynamic similarity between model and prototype, first that model and prototype should satisfy geometrical and kinematic similarity between them.
Yeah.
Okay. Now what is meant by dynamic similarity? Whatever the homologous points we have considered, at all those homologous points, these force ratios should be equal. Okay.
Mm-hmm.
As we have discussed, how many types of forces? 6 types of forces, isn't it?
Yeah.
Now all those forces should equal.
Mm-hmm.
So that is force in the model divided by force in the prototype
Yeah.
should equal to, okay, force in the model by force in the prototype. It is a ratio. This ratio should equal at all the homologous points, right?
Yeah.
And this is called as force scale ratio. This is called as what? Force scale ratio.
Mm-hmm.
This is in detail about model and similitude studies. Clear?
Yeah.
So if all these three similarities holds between model and prototype, then they are called as exactly similar, right?
Mm-hmm.
So let me write that point as well. If all the three if all the three similarities hold between the model and prototype, hold between model and prototype, then they are exactly similar. Okay.
Mm-hmm.
Now I'll give you a small question. Please try to solve this. A very small question I'll give you. A model is constructed on the basis of on the basis of Reynolds model law. Find the velocity find the velocity and discharge scale ratio in terms of length and kinematic viscosity scale ratio. So this question I'll explain, and next question I'll give you for you. Okay, you please practice it.
Yeah, and can you go to the other page for a second? I needed to finish
Yeah,
writing
just a
the.
moment. I'll go.
Mhm.
Previous page, right? This one.
Yeah,
Ah, yes.
right here. Similarities. Um, is that exactly similar at the
Yes,
end?
yes, yes. They
Okay.
are exactly similar.
Yeah. Okay, I got that.
Okay. Now here see, here model and prototype are constructed based on Reynolds model law, right?
Mm-hmm.
What is Reynolds model law? Reynolds model law is nothing but Reynolds number in model should equal to Reynolds number in prototype, right?
Mm-hmm.
And what is Reynolds number as discussed? It is rho V L by mu, isn't it?
Mm-hmm.
Of model is equal to rho V L by mu of prototype, right?
Yeah.
And one more thing we know that this mu is the dynamic viscosity, isn't it?
Yeah.
Dynamic viscosity by density is what? Kinematic viscosity, isn't it?
Mm-hmm.
Which is represented like this. Okay.
Yeah.
So let me write here. Since mu by rho is equal to nu. Okay. Now from this you
Mm-hmm.
see Vm by Vm into Lm by mu m. Nu m is equal to Vp LP by nu P, isn't it? Can I write like this?
Mhm. Yeah.
So I rearrange the terms, means I'll take this Vp, that is velocity in the prototype, to the denominator here. So Vm by Vp, can I write like this?
Yeah.
Vm by Vp is equal to mu m by nu m by nu P into 1 by Lm by Lb. Can I write like this?
Mhm.
So this Lp I have taken to the denominator of Lm.
Yeah.
So now we know that Vm by Vp is nothing but what? Velocity scale ratio, right?
Yeah.
And nu m by nu P is what? Kinematic viscosity scale ratio, right?
Mhm.
And Lm by Lp is the length scale ratio. So this is
Yeah.
the first part of the question.
Yeah. Is that VN?
What?
Is that an N? I can't read what that says.
Which one n? There is no
Like
n
in this,
here.
what does it say in the subscript of the V? Like in the box.
Is the velocity in model.
Oh, okay. Yeah, that's M.
This
Okay, I
is
see.
R ratio. So velocity in the model by velocity in the prototype is nothing but velocity scale ratio.
Okay, I see that.
Okay.
Mm-hmm.
Right. This is what the velocity scale ratio. So velocity scale ratio is equal to kinematic viscosity scale ratio divided by length scale ratio. Okay.
Yeah, I see.
Now
Okay.
discharge. So we know that discharge scale ratio is equal to area scale ratio into velocity scale ratio, right?
Yeah.
Then area scale ratio is nothing but length scale ratio square, and velocity scale ratio just now we have written as kinematic viscosity scale ratio by length scale ratio. Now this and this will get cancelled, and finally we are left with LR into nu R. Okay.
Yeah.
This is how we can express discharge scale ratio as well as velocity scale ratio in terms of length scale ratio and kinematic viscosity scale ratio. Clear?
Mm-hmm. Yeah.
Now, as I said, this question is for you. Come on, you please do it. I'll give you one more question. That is a practice for you, but you please do it now itself
Mm-hmm.
so that you
Yeah.
will get somewhat clarity. If Reynolds model law Froud's model law both are both are applicable. Both are applicable. Find the velocity. Find the velocity scale ratio discharge scale ratio kinematic viscosity scale ratio in terms of in terms of length scale ratio. Yeah, you please do this question. Don't worry, I'll explain you the solution, but I'll give you the time. Please do this question. Okay.
Yeah, just scale ratio, correct?
So yeah, see, first step of this question is same as that of previous question. Okay.
Yeah, yeah,
So
I
without
know.
much explanation, straight away I'll write this step. This step.
Yeah,
Okay. Whatever we
yeah,
got in our previous question, that is VR is equal to nu R by LR. That I'll take up. Okay.
yeah.
So it was mentioned as Reynolds number of model is equal to Reynolds
Reynolds
number of
number,
prototype. Okay.
prototype. Yeah,
So from this straight away we can write velocity scale ratio is equal to kinematic viscosity scale ratio by length scale ratio. Can I write like this? Let this be one.
yeah, we can.
Yeah, one more thing is given. Fraud number of the model
Yeah, that
is
as well.
equal
I've
to fraud number of the
of
prototype, isn't it?
prototype. Yeah, yeah. I've written that
Yeah.
as well
So what
before.
is fraud number? V by under root GL, isn't it?
Yeah, yeah.
So M,
That's what I have as well too.
yeah, M. So this suffix M represents model. Okay.
Yeah,
VP by under root GP by LP, isn't it? Be it a
uh,
model or
yeah,
prototype,
yeah,
acceleration due to gravity always remains constant, which is
yeah.
9.81 meter per second square, right?
Mm-hmm.
Therefore, this can be, that G can be cancelled.
Yeah,
This G and this G can be cancelled, right?
yeah,
Then I'll rearrange the terms. Vm by Vp is equal to under root Lm by Lp, right?
yeah.
So
That's
which
what I
is
had
written
as
as
well.
velocity scale ratio is
Yeah,
equal to,
I didn't know what to do after this part.
yeah, length scale ratio to the whole power 1 by 2, because square root is
Uh,
nothing but 1 by 2, right?
yeah, yeah. That's okay. That's where I was getting confused.
Okay, so let this be 2.
Oh wait. Can
Okay,
you give me just 1 second to just
yes.
1 second? We are, and then that is so VM over that the line scale ratio and that. Okay, yeah, I understand now. Yeah,
Okay,
yeah, yeah. Okay.
so now you see in this question, first is asking us what? Velocity scale ratio in terms of length scale, right?
Yeah, yeah,
Therefore, VR is equal to LR to the power 1 by 2. This is the answer to the first part of this question.
yeah.
Now, second part of this question is asking discharge. So,
Discharge.
QR
Yeah,
is equal to, we know the discharge formula is Q is equal to AV. Therefore, QR is
yeah,
equal to AR into VR, right?
yeah,
Now, what is AR? It is LR square, right?
yeah,
Now, what is VR? VR is nothing but LR to the power 1 by 2. Now, upon simplifying this, we are going to get as LR to the power 5 by 2. Okay.
yeah,
This is the second part
yeah,
of the question.
yeah.
Now, third part, if you observe, is asking,
It's kinematic velocity scale
yes,
ratio,
kinematic
viscosity.
viscosity. So, from
Yeah,
1 and 2, here are 1 and 2 for us. From Reynolds
yeah,
model and Fraud's model. Okay.
yeah,
Now, in place of VR, can I write LR power 1 by 2?
yeah,
Okay. So from 1 and 2, therefore I will write LR power 1 by 2 is equal to nu R by LR. Therefore, kinematic viscosity scale ratio is equal to LR into LR to the power 1 by 2, which is LR power 3 by 2, right?
mm-hmm.
Next. Yeah, that's it he is asking. Therefore, we have expressed all the three scale ratios in terms of length scale ratio. Velocity scale ratio is equal to Lr power 1 by 2. Length scale ratio is equal to Lr power 5 by 2. And kinematic viscosity scale ratio is equal to Lr power 3 by 2.
Mm-hmm.
Clear with this?
Yeah.
Yeah. So now let me take up the questions that are given in your notes. Okay.
Yeah.
Okay. This question you want.
Yeah.
Colonization of moon will require an improved understanding of fluid flow under reduced gravitational forces. The gravitational forces on the moon is one-fifth that of the surface of the earth. An engineer is designing a model experiment for flow in a conduit of the moon. The important scaling parameters are Froude number and Reynolds number. The model will be full scale. The kinematic viscosity of fluid to be used on moon is 2 into 10 power minus 5 meters square per second. What should be the kinematic viscosity? Okay. So see here, for this question, as given, both Reynolds model law and Froude's model law are used. Okay.
Mm-hmm.
So without wasting much time, as per our previous two questions, see, previous two questions. So in this question, as per Reynolds model law, velocity scale ratio is equal to what it is? It is the ratio of viscosity, kinematic viscosity
Viscosity,
scale ratio by length scale ratio, isn't
length
it? Can
scale
I write that
ratio.
one?
Yeah. Yeah.
So VR velocity scale ratio is equal to nu r by Lr, right? Now in this question some informations are given. You please read this last but one line of the question. The model will be full scale. What does it mean?
The
That
model will
means
be like,
length of the model is equal to length of the prototype, which is equal to implies length scale ratio is 1. Okay.
mm-hmm.
That is the meaning of the model will be full scale, right?
Yeah.
And one more information was given. The gravitational force on moon is one-fifth of the surface of the earth. That is gravitational force on moon. So here
Yeah.
we are preparing model on the earth. Therefore, we are having prototype on moon, right?
Yeah.
So gravitational force means acceleration due to gravity on in prototype is one-fifth of the gravitational force on earth. That is in model. Okay.
Yeah.
Therefore, gr is equal to what? Gm by gp, isn't it?
Yeah.
Which is equal to 5. Okay.
Yeah.
So this is the result we got from Reynolds model law, right?
Yeah.
Whereas by making use of Froude's model law, Fe in the model, Fr, not Fe, sorry, is equal to Fr in the prototype. Okay.
Mm-hmm.
Here model is on the earth. So Vm by under root Gm by Lm is equal to Vp by under root Gp into Lp. Clear?
Mm-hmm.
From this we can write Vr is equal to. So is here it is on moon and earth. Therefore this G and G will not get cancelled. Please make a note of it.
Yeah. Yeah.
Then here GR LR under root. Can I write like this?
Yeah.
So GR is equal to what? 5. Just now we have written here. And LR
Yeah.
is equal to 1. Therefore, VR is equal to what? Root R. Isn't it?
Yeah.
Sorry, root 5.
Root 5. Yeah.
Right. So coming back to this equation, the first one. So VR is what? Root 5 is equal to nu R.
Yeah.
Because you see, LR is 1. Therefore, nu R is nothing but kinematic viscosity in model by kinematic viscosity in prototype is equal to root 5. Now, if you observe in the question, kinematic viscosity of the fluid on the moon means prototype is given. Now, he's
Yeah.
asking us kinematic viscosity for model on earth, that is nu m is asking. Root
Yeah.
5 into 2 into 10 to the power minus 5. Can you simplify and tell me this answer?
Yeah, let me just use a calculator. Just a second. Uh, minus root 5. 4.47214 times 10 to the power of negative 5.
4.47
472114.
2. Okay, leave it.
Yeah, you don't have to do it all the
Yeah,
way.
is this the answer for
Yeah.
this question?
Yeah.
Yeah, that's it. So see, whatever the questions I have given to you as
Mm-hmm.
an example, the same this question is based on the same concept,
Yeah.
right?
Mm-hmm. Yeah.
Any other doubts?
Uh, just 1 second. I can
Yeah,
go
yes,
through.
you can go through it. Okay, let me scroll it from top to bottom one more time. This is the beginning of your topic.
Mm-hmm.
Better once you please go through this PDF quickly. If at all any doubt is there, let me know so that I'll try to clarify it. Even though I
Yeah.
completed the total topic, but once you please go through this your PDF, because here I
Yeah.
explained you in my style, but this is your
Yeah.
own PDF from which the concepts are expected to be understood and you are supposed to follow this.
Yeah.
So please go through it quickly as it is of 9 pages. Please go through it quickly because all the concepts already we have discussed.
Mm-hmm.
So
Okay.
please make
So
it fast from the first
yeah.
page to ninth page.
Yeah. Okay, I'll go through it right
Yeah.
now then.
And let me know any doubt from your end.
Yeah.
As I displayed this on the screen, yeah, you please go through it fast.
I have it out on my iPad as well.
Sorry.
I have it on my iPad as well, like the
Okay, yeah,
PDF document.
anything as per your convenience, anything you can do.
Yeah. Mm-hmm. Okay, I'll go through it quickly. Geometric similitude means that model. My teacher kind of displayed it a little bit complicated, but then now I read it and I kind of understand it now.
Okay, okay.
Yeah, I have sent like what my teacher has done for those ones because it's blank on your document.
Okay.
And then I sent you what my teacher has done. I just looked over it and then I kind of understand it now.
Yes, yes. So first you please refer our notes, our PDF.
Yeah,
It
yeah,
will be in simpler terms.
yeah. I
It is a
noticed that.
simplified version. So first you please go through it and later you can go through your teacher's notes. Then you can easily identify
Mhm.
it.
Yeah, that's what I noticed as well. And yeah, I got everything. I sort of understand a little bit.
Yeah. So this is
Yeah,
all about dimension analysis. Clear?
yeah. That's all dimensional analysis. Yeah.
Yes. So next topic, I think you want.
Just start momentum today, then we can, because I also want a lesson tomorrow.
Okay.
So we can just start momentum today, get as much as we can done, and then we can continue tomorrow.
Yes, yes, definitely, definitely. So this is what the PDF you have, right?
Yeah. The My teacher said she was gonna release the filled out version of the PDF today.
Okay.
We just didn't have enough time to go over it in class.
Okay.
She said that the filled out version would be released today, so whatever that we can't cover on the PDF, I can just see on the PDF that she releases today as well.
Yeah. Is there any other PDF? Is there any other PDF?
No, no. This She just released an empty one. She said she's gonna give us the filled one today, and
Okay.
then yeah,
Asha, this is empty one, right?
yeah, empty one.
Okay. Okay. So.
He still
Uh,
has to make the notes still. That's why.
okay. Okay. So when she will give
Yeah,
the full PDF tomorrow?
she'll give it today, tonight. She's gonna
Asha.
upload it on our course page tonight.
Okay. 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 No issue.
Before the night, she said she'll upload.
Okay. Okay. So see.
Hmm.
Okay. Anyhow, we'll discuss about here the things that are mentioned. So linear momentum equation, or you can say theory and application. So this particular momentum equation describes the theory of linear momentum equation, and this equation is an important tool. Okay, is an important tool to solve so many number of problems. What are those problems? Let us try to understand.
Hmm.
Before that, so theoretical basis of linear momentum equation. What is the theoretical basis? Let us try to understand. Basically, from physics, what is meant by moment? Can you please tell me what is meant by moment?
In physics,
Yeah, in physics, yes, exactly. Momentum,
moment in
not moment,
physics,
momentum. What is meant by momentum in
momentum,
physics?
momentum or moment.
Momentum, momentum, not moment. Correction.
Oh, oh, I thought you were saying it's like mass in motion. That's what we called it.
So,
Like
momentum,
objects that,
yeah, listen,
like if an
momentum is
object's
nothing
moving,
but
then they have
product of
momentum.
mass into velocity.
Yeah. Oh, like the formula.
Yeah,
I thought you meant like the meaning.
okay, okay. So, meaning is nothing but it is the product of mass into velocity.
Yeah, which is
Okay,
mass in motion.
mathematical meaning.
Yeah.
That is a momentum basically, right?
Yeah.
So from the RTT means Reynolds transport theorem, we can derive that momentum equation for a closed system.
Mm-hmm.
We know this formula by definition. So see, whatever I written here, B is equal to B by small b is equal to capital B by mass. Therefore,
Yeah.
here capital B is what? Momentum. Small b is
Yeah.
what? Velocity and mass, right?
Mm-hmm.
So when B is equal to V bar, that is what he written. When B is equal to V bar, small b is equal to V bar, capital B becomes momentum and the Reynolds transport theorem. So what this Reynolds transport theorem tells us? The rate of change in momentum with respect to time. Okay, this is what dB system by dt is nothing but the rate of change in momentum with respect to time is equal to the rate of change in momentum with respect to control volume plus the rate of change in momentum with respect to control surface. Here CV is nothing but control volume, whereas CS is nothing but control surface.
Yeah.
Okay.
Mm-hmm.
Therefore, the rate of change in momentum with respect to time is nothing but summation of rate of change in momentum with respect to control volume and rate of change in momentum with respect to control surface. Clear?
Mm-hmm.
then we can make use of Newton's second law of motion. So what is Newton's second law of motion? The rate of change in momentum is equal to external force acting. Clear?
Mm-hmm.
Hence, the very same thing can be written as, so summation includes the all forces that are acting. So sigma F is equal to which is equal to d by dt control volume b rho dv plus control surface b rho v bar into dA. Okay.
Yeah.
So this is how we can write the momentum equation. So this is the momentum equation as per Reynolds transport theorem, and by making use of Newton's second law of motion, this is how we can write it.
Yeah.
Okay.
Mm-hmm.
So this momentum equation can be stated as the resultant force acting on a control volume is equal to the time rate of increase of linear momentum within the control volume plus net efflux of linear momentum from the control surface. Okay.
Yeah. Yeah.
So let me write that statement.
Mm-hmm.
Okay. Let me write that statement.
Yeah.
Here I'll write.
Yeah. Yeah.
Clear now?
Yeah.
So whatever I have written or we have discussed in mathematical form, the same mathematical form have put it in the statement.
Mm-hmm.
So can you please read it out, the statement what I have written?
Yeah. The resultant force acting on a control volume is equal to the time rate of increase of linear momentum within the control volume plus the net of
Net efflux, net efflux.
net efflux of linear momentum from the control sample.
Yeah.
What does a net of flux mean?
Yeah, flux is nothing but momentum per time.
Yeah, okay.
So here this is the momentum. Now this momentum is divided with time, then that is known as a flux.
Yeah.
Okay.
Mm-hmm.
So this is m dot v.
Yeah. Oh, okay.
Okay.
Yeah. That's we just call it m dot v. We don't
Yeah, yes,
use a
yes, yes,
flux or
yes.
anything. Yeah.
Okay. Now the first term and the second term we can simplify this. Simplify. Okay.
Mm-hmm.
Now let us see the application of that momentum equation.
Yeah.
So let us calculate the momentum accumulation in the control volume. Say there is a nozzle and we pick one small volume inside the control volume, and the momentum in this small volume is rho delta v bar, right?
Yeah.
So total momentum inside control volume is the sum of all control volumes. That means we need to integrate it.
Yeah.
So taking the time derivative, we get the rate of change in total momentum. Okay.
Mm-hmm.
So with the questions, we can understand this very clearly rather than with theory. Okay.
Yeah.
Are you clear?
Yeah.
So here you need to understand or you need to remember this fundamental statement. Okay, this fundamental form and statement.
Yeah.
So this fundamental form only we are going to simplify it. Nothing more than that.
Yeah.
Now let us see what are the problems that we can solve by using this momentum equation. And you see here it was given very clearly applying the momentum equation. So for applying the momentum equation, follow these steps. First, analyze the system. Okay, this is the first step. Identify the control volume. Second step, draw the force and momentum diagrams. Draw down momentum equation for the system. Solve the equation for x direction and equation for y direction. That's it.
Mm-hmm.
Here example was given. You take this example.
Yeah.
Here you say this water is passing through the pipe bend. Okay,
Mm-hmm.
here the pipe bend is there. Now the entry, let one be the entry and two be the exit of the pipe bend. Okay,
Yeah.
one be the entry and two be the exit.
Mm-hmm.
So for this pipe bend, you please first draw the control volume. So here the system is what? Our system is pipe bend. As we have analyzed the system, after analyzing the system, identify the control volume. Now the shape of exactly similar to the shape of this pipe bend, you draw the shape of control volume.
Mm-hmm.
Okay. For this control volume, you represent the force diagram, means the various forces that are acting in x and y direction.
Mm-hmm.
And for the same control volume, you represent the moment as well at inlet and outlet, or you can say at entry and exit.
Yeah.
Now use
Okay.
Newton's second law of motion and solve in x and y direction. That's it.
I see.
Yeah.
Oh,
It means you see, I'll give you the simplified form
yeah.
of momentum equation. So
Yeah.
finally, F bar comes out to be m dot v1 minus v2. This is how it can be modified.
Oh,
It means
okay.
Fx, force in x direction, is equal to m dot Vx1 minus Vx2.
Vx2.
And in the same way, force in y direction Fy is equal to m
M
dot.
dot Vy1 minus Vy2.
See, sometimes this suffix may interchange. Here it comes 2, 1
Yeah.
and 1, 2. It depends, okay? Depending upon the system, this 1, 2 suffix may change. Clear?
Yeah. Okay.
So this is a simplified form of the momentum equation in a nutshell.
Yeah.
Okay?
Yeah.
Now you see a roadmap for problem solving. So what are the problems we are having? We are having two types of problem. One is stationary control volume and another is moving control volume.
Yeah.
Now what are the examples where the control volume is stationary? When water is coming out of the jets and hitting the vane, like
Yeah.
in case of turbines.
Yeah.
In turbines, the jet comes out of the nozzle and it hits the vane. There
Yeah.
also, there we are having stationary control volume.
Mm-hmm.
And the water which is coming out of the nozzle, and or you can say the water which is passing through the pipe bend,
Mm-hmm.
and water moving with variable velocity. So these are the examples of stationary control volume.
Yeah.
Whereas
Okay.
examples of moving control volume are constant velocity as well as accelerating one.
Mm-hmm.
So please remember these practical scenarios where we can make use of momentum equation. So
Yeah.
momentum equation, basically momentum equation will solve two kinds of problem. One is related to the stationary control volume and another is related to the moving control volume.
Yeah.
Now examples also there we have written clearly, right?
Yeah.
Now you see linear momentum equation for stationary control volume. So what is meant by stationary? Stationary means not moving, right?
Not moving. Yeah.
At rest. Stationary means at rest.
Yeah.
Now in this case, what are the scenarios and how to solve this? Let us see. So here, what we learn, calculate momentum in stationary control volume for a range of problem, that is fluid jet, etc. Now coming to the fluid jet. What are fluid jets? These types of problem involve a free jet leaving a nozzle. However, we do not focus on nozzle itself. For example, we want to find the tension in the cable that holds the cart. So see here. Okay.
Yeah.
So now solving tips. How to solve this question? When a free jet crosses the control surface, the jet does not exert a force. So there is no need to draw a force on force diagram. The momentum flow of the jet is m dot v, right?
Yeah.
Okay, so see first point, when a free jet crosses the control surface. So obviously here the dotted portion is the control surface. Okay.
Mm-hmm.
So see here, in our example, here this is the cart and this cart is held in position by a cable. And on the top
Yeah.
of this cart, we are having a nozzle which is issuing the jet.
Yeah.
Now you see in this diagram, the dotted lines or this dotted one is representing control surface.
Mm-hmm.
So when a free jet crosses the control surface, the jet does not exert a force. So there is no need to draw a force on the force diagram. Okay.
Mm-hmm.
See, it means here in the generalized discussion of solving the problem, here you see the third one, draw the force and momentum diagram. That is the third step, right?
Yeah.
But here, when the free jet is leaving the control surface, then that jet will not exert any force. Therefore, no need to draw the force diagram. Please make a note of it.
Okay.
Now, one more
Mm.
question is also given here based on that. So, a balloon rocket is held in place by a force. So, see here, this is the balloon rocket and this balloon rocket is held in position by a force F. The pressure
Mm-hmm.
inside the balloon is 12 inch H2O. Okay, in terms of H2 it was mentioned. Okay, 12 inch H2O. The nozzle dia is zero point 0.4 centimeter. The air density is 1.2 kg per meter cube. Find the exit velocity V and the force F. Neglect the friction, weight of the balloon, and assume the airflow is inviscid and irrotational. Okay.
Mm-hmm.
The control volume is the entire balloon rocket. The force diagram shows only one force, that is to hold the balloon. So here in this case also, the water is coming out of the balloon. It means here it is a free jet coming out of crossing the control surface. Therefore, this jet will not exert any force. However, to keep this balloon in position, initially we have applied some force. Therefore, in the force diagram, except this given force, no other force will act.
Yeah.
Okay.
Okay.
So based on that, we can solve this question.
Yeah.
Okay.
Mm-hmm.
So next part. Next is the vanes. So as I said, mainly these vanes are observed in turbines, and even in our households we are having fan, right?
Yeah.
That fan will have wings. Therefore, those wings can also be considered as vanes. And one more
Yeah.
example, you take the exhaust fan.
Yeah.
So for that exhaust fan also we are having a wings, isn't it?
Yeah.
Those wings can be considered as vanes.
Yeah.
And one more example
Yeah.
you see in this diagram, for a ship or boat we are having a sail. That sail is
Mm-hmm.
also considered as vane.
Yeah, because of the wind directing the cloth of the
Exactly.
ship directing the wind.
Yes, exactly. So see here definition of vane and everything is given. A
Yeah.
vane is a
Okay.
structural component that is used to turn a fluid jet. Okay.
Yeah.
That fluid might be a water, or else that fluid might be a air, whatever it might be. Okay.
Yeah.
Next. So examples of vanes are given. A blade in a turbine, a sail on a ship, and a thrust reverser on an aircraft engine, whatever it may be. All these are the examples of vanes. Okay.
Yeah.
Now,
Yeah.
whenever vane problems are involved, in those vane problems, along with momentum equation, we need to make use of Bernoulli's energy equation as well, which is what we
Yeah.
have discussed in our first class, right?
Yeah.
So, in solving the vane problems, first we need to make use of Bernoulli's equation. So, please tell me the Bernoulli's equation.
Bernoulli's equation, the energy equation,
Yeah, Bernoulli's energy equation.
that was the oh, I forgot.
Here I
Just
am writing P1 by gamma plus V1 square
oh,
by 2G plus Z1 is equal to.
yeah. P2. Then we can also split this into the pressure head, the other head, correct?
Sorry.
Wait, I'm trying to just 1 minute.
So this equation, of course, I have derived and explained you.
Mm-hmm. Yeah.
So now in this equation, we need to assume V1 is equal to V2.
Yeah. Okay.
Okay. Next, the momentum flow is equal to m dot V1 as already known to us.
Mm-hmm.
If the vane is flat, we can assume force that holds the vane is normal to the surface, normal to the vane.
Yeah.
If the jet does not exert a force across the control surface.
Yeah. Okay.
Okay. So these are the few points you need to keep in mind when solving the questions. If it is a free jet, then we have discussed the solving tips. Now it is for vane. For vane, we need to use Bernoulli's energy equation as well, along with momentum equation. Okay.
Mm-hmm.
And here the question is there. So these all questions first you try by the solving tips, and anyhow we'll discuss in detail. Okay.
Yeah.
In our next class, I'll explain.
Yeah.
So next problem is related to the pipe bends. Okay.
Yeah.
Here is the pipe bend. So whenever the direction of flow of the water has to be changed, then the pipe bend is being introduced.
Yeah.
So see here, a pipe bend is a structural component that is used to turn through an angle. A flange is a round disc with a hole in the center that slides over a pipe and is often welded in place. Flanges are bolted together to connect sections of pipe. Okay.
Mm-hmm.
Generally, to connect a pipe bend to the pipe, we use flanges.
Yeah.
Now, solving tips you see, the momentum flow equals m dot vi. For example, m dot va is the inflow and m dot vb is the outflow, as I already discussed, entry and exit of a pipe bend, right?
Yeah.
Therefore, at the entry we write m dot va and at the exit we write m dot vb. And even in the
Yeah.
direction of x and y also we write this m dot va and m dot vb. Okay.
Yeah.
Now, the next point or the next solving tip here is include a pressure force where the control surface cuts through the pipe. For example, pressure force at A and B are pressure at A multiplied by area at A and
Yeah.
pressure at B multiplied by area at B, because pressure, what is the formula for pressure? Force upon area. Therefore, pressure force is equal to intensity of pressure into area, right?
Mm-hmm.
Hence, along with the momentum at the inlet and outlet, here we need to write the pressure force as well.
Yeah.
After that, apply Bernoulli's equation. Just now I explained you what is Bernoulli's equation. And by writing the
But
Bernoulli's equation, we can relate pressure at A and B. This
yeah.
assume no energy loss. We will revisit the assumption in chapter 7. So already we have
Yeah.
discussed this, right?
Yeah.
So after that, here one more equation to be used, that is continuity equation. So see,
Yeah.
slowly complication is increasing. It means in the free jet,
Yeah.
we have used only momentum equation, right?
Mm-hmm.
Whereas in case of vanes, we have used momentum equation along with energy equation.
Yeah.
Now in pipe bend, we are using momentum equation, energy equation and continuity equation.
Yeah.
So when the CS cuts through a
Yeah.
support structure like a pipe wall, represent the associated force on the diagram. So this time
Yeah.
we need to represent the force as well.
Yeah.
This is what the third kind of problem involving momentum equation. Okay.
Mm-hmm.
So how many kinds of problems we have discussed it so far? One is free jet,
Yeah.
vane. Second is vane, and third is pipe bend.
Pipe bends. Yeah.
And all these three categories will come under stationary control volume.
Stationary.
Okay,
Yeah.
because the control
Yeah.
volume is not moving here.
Yeah.
So next one is the nozzle. So
Yeah.
nozzle is also stationary control volume. Okay.
Yeah.
Now, what is nozzle? You see, nozzles are the flow devices used to accelerate a fluid stream by reducing the cross-sectional area of the flow. This type of
Mm-hmm.
problem involves analysis of a nozzle itself, not the analysis of the free jet. Okay.
Yeah.
So here, nozzle means at the end or at the exit, diameter of that pipe is being reduced so that velocity increases and the flow will become accelerated, right?
Mm-hmm. Yeah.
Therefore, in this case, we analyze nozzle itself. You see the shaded portion. Here we are
Yeah.
analyzing nozzle itself, but not the jet coming out of the nozzle.
Yeah. Okay.
So, hence this comes under uh, moving control volume. Okay.
Moving. Yeah. Yeah. Moving.
So, let us see the solving tips.
Mm-hmm.
The momentum flow equals m dot v1. For example, m dot va as inflow and m dot vb as outflow for the figure above. The same as that of pipe bend. Okay. For a pipe bend,
Mm-hmm.
how do we have written? Okay. How do we have written momentum flux at inlet and outlet? In the same way, for the nozzle also, we need to write it.
Yeah.
Second step also almost same. Include a pressure force where the nozzle is connected to the pipe. For
Yeah.
example, pressure force at A. Next,
Mm-hmm.
apply Bernoulli's equation to find PA. Next, apply continuity equation and relate VA and VB. When the CS
Yeah.
cuts through a support structure like a pipe wall, represent associated force on the diagram. That's it.
Yeah. Okay.
So more or
Oh.
less the procedure is same as that of pipe bend, but only the only thing here is here we need to consider the nozzle itself, but not the free jet.
Yeah. Oh.
That's it.
Okay.
Rest everything is same. The same steps what we have discussed for the pipe bend. Okay.
Yeah. Okay.
Next. So next here is moving control volume. Okay, this is the correct scenario for moving control volumes. Okay.
Yeah.
Now in this moving control volumes, what we will discuss. So here we'll discuss the calculation of the momentum in non-stationary control volume for a range of problems.
Yeah.
So as here the control volume is moving, therefore the reference frames we need to take. So what are those reference frames? Let us try to understand here. The linear momentum equation is not valid for an inertial reference frame. We first need to define a reference frame to describe a moving object. A reference frame is a framework where an observer takes the measurement. Inertial reference frame, stationary or moving with constant velocity.
Yeah.
Non-inertial reference frame, it is accelerating.
Mm-hmm.
Okay. Now see the example. A water jet pushes a block with a constant speed. So that is example of moving control volume. So see here in this diagram, are you able to see the diagram? In
Yeah.
this
Yeah.
diagram, the water jet is coming out of the nozzle and this water jet is continuously striking this block with a
Mm-hmm.
constant speed. But this water jet is trying to push the block. Therefore, the
Yeah.
control volume is not constant or stationary.
Mm-hmm.
Okay.
I see.
So for this,
Yeah.
what we need to do? So he is asking us compute the frictional force F acting on the block between block and the ground, so that this block will remain stationary even though it is being acted upon by jet force.
Yeah.
Now two different methods to solve this. What are the two different methods? One is moving reference frame and another is fixed reference frame.
Yeah.
So in
Okay.
moving reference frame, this is the moving reference frame. Okay. And the
Yeah.
other is a stationary fixed reference frame.
Yeah.
Next. So here is the fixed reference frame. So in fixed reference frame, the ground is taken as fixed. Okay, with respect to ground, we carry out the calculations.
Yeah.
Next. Yeah, this is what the question, this is what the momentum equation or momentum concept in a nutshell.
Yeah.
I think almost we have completed 2 hours, maybe 10 minutes less, right?
Like I have to take a ship. I have to take a ferry in like 4 minutes. So I have to leave in like 5 minutes at most.
Sorry, I didn't get you.
I have to leave in like 5 minutes.
Yeah, okay, yes, 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 yeah.
Yeah.
Yes, already we have
So
completed this momentum equation, right?
yeah.
We'll discuss about this momentum equation after completion of the class. Before
Yeah.
class, whatever is required, that overview I have given so far.
Yeah.
We'll discuss this momentum equation after your class, once your class is done.
Yeah. Yeah.
Okay, so now
Okay.
we can stop this session, right?
Yes. Yes.